Hello everyone, my name is Davud. I'm from Iowa State University in United States. My presentation is about distributed non-convex optimization. This is a joint work with my advisor, Dr. Mingyi Hang and Mingming Zhao from Zhejiang University in China. First, let me give you a brief introduction of what is distributed optimization. In distributed optimization, we have a network of agents like this picture, and each agent contains a local cost function denoted by Fi. However, the agents have only a partial knowledge about the entire problem. It means that no one knows the entire problem. And typical optimization model for distributed optimization problem is minimization over x, summation of I from 1 to n, which n denotes the number of agents in the network, and Fi of x. The key objective of agents in the network is two things. Number one is to achieve consensus about the optimization variable with the neighbors, and second is to optimize the global objective function. So let's see why this is an important problem, why we should study distributed optimization problem. First, let's consider the data optimization problem, like this. In this data optimization, the data points are collected using different agents in different parts of the world. On the other hand, it is infeasible or inefficient to collect all of data in a central controller, in a central node. So in this way, we have to do distributed optimization. Second issue is about the data volume. Look at this graph. This graph is showing the prediction for the volume of data in the future. So you see that it is growing very fast. For example, it is predicted that in 2025, the volume of data would be 180 zettabyte, which is 180 followed by 21 zeros. So in the future, it is impossible to do central computations in many cases. So we have to do distributed computation. So now let's see what is the motivation for our study, which is non-convex distributed optimization. Let me give you an example. The example is distributed binary classification. So in distributed binary classification, we have a network of agents like this. The agents are sensors, and each sensor collecting some data, and the agent contains this local cost function. This function is a non-convex function. So the question is that, can we apply the existing distributed convex algorithms for this problem? And unfortunately, the answer is no. So for example, we have applied the DSG algorithm, one of the first algorithms for distributed convex problems, and you can see the results. So for different step sizes, we have shown that the algorithm is not going to converge. So the challenges and open questions in this area are the following. First question is that, can we apply the algorithm that has been designed for convex distributed optimization problems to the non-convex cases? Second question is that, is there any convergence guarantee for the proposed algorithm? And third, how fast is the algorithm? What is the convergence rate for the algorithm? Considering this question, our contribution is the following. First, we design an optimization algorithm to solve distributed non-convex optimization problem. Then we provide convergence analysis and rate of convergence for the proposed algorithm. So let's quickly review the literature in this area. So the literature is divided into two important parts: convex case and non-convex case. In convex case, the literature is very extensive. So I just pick a few more relevant papers in this part. So first, consider this fully distributed network. So in fully distributed network, we have some nodes that they are connected together, and we do not have any particular node in the network. All nodes are identical. Okay. So one of the first algorithms for this problem is called decentralized subgradient. This algorithm is diminishing step size to converge to the global solution. This is not very good. And also the convergence rate for this algorithm is log of r over square root of r, which is very slow. Later, in 2015, extra algorithm has been designed, which leverages the information of past 2 iterations. So the convergence rate for this algorithm is 1 over r, which is much faster than the previous one. However, this algorithm works only for convex problems. So it cannot be applied for our problem in non-convex case. Another set of papers in the convex area are related to this network. So in this network, we have a central controller and the other nodes are connected to the central controller. This network is more popular in machine learning community, and there are some algorithms to solve the optimization problems over this network. We have ADMM algorithm, DANE algorithm, and DISCO algorithm, and so on. But in non-convex cases, the literature is very scant. So we have only a few algorithms. We have dual subgradient, ADMM, next algorithm, and next algorithm. However, there is a gap in the literature. The gap is that for non-convex, fully distributed optimization, there is no algorithm with provable convergence rate. So in this research, we're going to fill this gap. So let's go to the next section, which is about the algorithm. So here is the contribution of our paper. First, we propose a primal-dual algorithm, which is called Prox-PDA, for non-convex problem over a fully distributed network. Then we provide convergence analysis and rate of convergence for this algorithm. And finally, we provide some variants of the Prox-PDA to facilitate the performance of the algorithm. Okay, so first let's see the formulation of the problem. First of all, the network that we have considered is an undirected, static, and connected network. So we reformulate the problem in the following. We split the variable x, which is a global variable among all agents, into xi. So we define a local copies of variable x. So now we have minimization of fi of xi instead of fi of x. Each agent has its own variable. However, we need to have consensus with the neighbors. So we add this constraint, xi minus xj equals to 0 for every edge in the network. Further, we can simplify this reformulation by defining some new notations. For example, if we stack all the variables xi into x and define fx as the summation of fi of x, and also if we define an incidence matrix, which is defined this way, we can reformulate the problem 1 to 2. So these two are equivalent. Actually, in incidence matrix, for each edge we have a row in the matrix, and for each node we have a column. So, for example, this edge is related to the first row, and since it's connected node 1 to node 2, we have 1 in node 1 and minus 1 in node 2. Okay, this is the algorithm. Our algorithm is an augmented Lagrangian based algorithm. So first we need to define the augmented Lagrangian, which is f of x plus mu times ax. Mu is the due variable, and this is the augmented term. Suppose that B is a pre-selected matrix. This is the algorithm. In the first step, we update the primal variable by minimizing the augmented Lagrangian plus this proximal term. And then we update the due variable. So this is the primal dual algorithm. This proximal term is very important in our algorithm because it ensures two important things. First, it makes the problem strongly convex, and second, it makes the problem decomposable over all different variable blocks. Okay, so let's see how it works. So if we define sign and sign left Laplacian matrix in this way, and define matrix P as the component-wise absolute value of matrix A, we can see that the variable x can be written in this way. So the first term is decomposable. This is linear, so it is decomposable. This one is decomposable, and this red term is also decomposable because matrix D is a diagonal matrix. D actually is the degree matrix. Now let's see the convergence analysis for this algorithm. We have some assumptions. These assumptions are very common in non-convex optimization. First assumption is that f is an L-smooth function, and also we pick matrix B such that A transpose A plus B transpose B is greater than identity, and this function f of x plus this term is lower bounded. So in the first lemma, we bound the descent of the augmented Lagrangian. So if all the assumptions are satisfied, we have this bound for LB minus LBR plus 1 minus LBR. Okay, so we can see that this coefficient in front of XR plus 1 minus XR can be negative if the peak beta are large enough. However, this coefficient cannot be made negative no matter how big beta are. Okay, so we have to look for a different term, and this augmented Lagrangian cannot be served as a potential function. So it turns out that this red term is our desirable term. Okay, so in this lemma, we can see that this term is decreasing in terms of WR and increasing in terms of XR plus 1 minus XR. So it's basically behaving in an opposite manner of the augmented Lagrangian. And surprisingly, a conic combination of the augmented Lagrangian and this red term decreases in each step. So we define the potential function as the summation of the augmented Lagrangian plus this term. So in this lemma, if all the assumptions are satisfied, the potential function is decreasing as long as beta and C are picked appropriately. And also we can simply show that this potential function is lower bounded. So the potential function is decreasing and lower bounded. So if we define the optimality gap as the summation of the primal gap and the due gap, we can check that if this Q goes to 0, the limit point of the algorithm is the KKT point of the problem. This is the main theorem. So the first bullet shows that we get the consensus solution among all agents. The second bullet shows that the limit point of the algorithm converges to the KKT point. And the last bullet is about the convergence rate. Actually, we proved that our algorithm converges in a sublinear manner. In this slide, I have some variants of the Prox-PDA. In the first variant, which is Prox-PDA IP, I used an increasing step size instead of a constant step size. And in the second one, I solved the primal problem in an inexact manner. I don't have to go through the details of this variant. So now let's see some interesting connections between our algorithm and some primal only algorithm. So we can show that our primal dual algorithm can be written as the following primal only algorithm. So this is the primal only form of our algorithm. And interestingly, this form is exactly the same as extra algorithm, which extra has been designed for convex problems. So using our analysis, now we can say that the extra can work for non-convex optimization problems as well. Let me give you some numerical results. So we consider distributed binary classification problem, and we measure the optimality gap and the constant violation, and compare our algorithm with DSG and distributed percent. This is the result. This red dashed line and this blue line are our algorithm. And you can see that in both cases our algorithm is much faster than this two algorithms. In conclusion, in this one we propose a primal-dual algorithm to solve a non-convex distributed optimization problem. We provide convergence analysis and rate of convergence for this algorithm. And finally, we have found an interesting connection between extra and our Prox-PDA algorithm. Thank you very much.